a WikiVidi Documentaries production. Don't forget to like and subscribe. Enjoy. Raman scattering. Raman scattering, or the Raman effect, is the inelastic scattering of a photon by molecules which are excited to higher vibrational or rotational energy levels. It was discovered by C.V. Raman and K.S. Krishnan in liquids, and independently by Grigory, Landsberg, and Leonid Mandelstam in crystals. The effect had been predicted theoretically by Adolf Smekal in 1923. When photons are scattered from an atom or molecule, most of them are elastically scattered, such that the scattered photons have the same energy as the incident photons. A small fraction of the scattered photons are scattered inelastically by an excitation, with the scattered photons having a frequency and energy different from, and usually lower than, those of the incident photons. In a gas, Raman scattering can occur with a change in energy of a molecule due to a transition to another energy level. Chemists are primarily concerned with this transitional Raman effect. History. The inelastic scattering of light was predicted by Adolf Smekal in 1923. In 1922, Indian physicist C.V. Raman published his work on the molecular diffraction of light, the first of a series of investigations with his collaborators that ultimately led to his discovery of the radiation effect that bears his name. The Raman effect was first reported by C.V. Raman and K.S. Krishnan, and independently by Grigory Landsberg and Leonid Mandelstam, on the 21st of February 1928. Raman received the Nobel Prize in 1930 for his work on the scattering of light. In 1998, the Raman effect was designated a National Historic Chemical Landmark by the American Chemical Society in recognition of its significance as a tool for analyzing the composition of liquids, gases, and solids. Degrees of freedom. For any given chemical compound, there are a total of 3 n degrees of freedom, where n is the number of atoms in the compound. This number arises from the ability of each atom in a molecule to move in 3 different directions. When dealing with molecules, it is more common to consider the movement of the molecule as a whole. Consequently, the 3 n degrees of freedom are partitioned into molecular translational, rotational, and vibrational motion. 3 of the degrees of freedom correspond to translational motion of the molecule as a whole. Similarly, 3 degrees of freedom correspond to rotations of the molecule about the x, y, and z axes. Linear molecules only have 2 rotations, because rotations along the bond axis do not change the positions of the atoms in the molecule. The remaining degrees of freedom correspond to molecular vibrational modes. These modes include stretching and bending motions of the chemical bonds of the molecule. For a linear molecule, the number of vibrational modes is 3n3 to 3n5, whereas for a nonlinear molecule the number of vibrational modes are 3n6. Molecular vibrations and infrared radiation. The frequencies of molecular vibrations range from less than 1012 to approximately 1014 Hz. These frequencies correspond to radiation in the infrared region of the electromagnetic spectrum. At any given instant, each molecule in a sample has a certain amount of vibrational energy. However, the amount of vibrational energy that a molecule has continually changes due to collisions and other interactions with other molecules in the sample. At room temperature, most of the molecules will be in the lowest energy state, which is known as the ground state. A few molecules will be in higher energy states, which are known as excited states. The fraction of molecules occupying a given vibrational mode at a given temperature can be calculated using the Boltzmann distribution. Performing such a calculation shows that, for relatively low temperatures, most of the molecules occupy the ground vibrational state. Such a molecule can be excited to a higher vibrational mode through the direct absorption of a photon of the appropriate energy. This is the mechanism by which IR spectroscopy operates. Infrared radiation is passed through the sample, and the intensity of the transmitted light is compared with that of the incident light. A reduction in intensity at a given wavelength of light indicates the absorption of energy by a vibrational transition. The energy, E, of a photon is a/nu, where h is Planck's constant and /nu is the frequency of the radiation. Thus, the energy required for such a transition may be calculated if the frequency of the incident radiation is known. Raman scattering. It is also possible to observe molecular vibrations by an inelastic scattering process. In inelastic scattering, an absorbed photon is re-emitted, with lower energy. The difference in energy between the incident photons and scattered photons corresponds to the energy required to excite a molecule to a higher vibrational mode. Typically, in Raman spectroscopy, high-intensity laser radiation with wavelengths in either the visible or near-infrared regions of the spectrum is passed through a sample. Photons from the laser beam produce an oscillating polarization in the molecules, exciting them to a virtual energy state. The oscillating polarization of the molecule can couple with other possible polarizations of the molecule, including vibrational and electronic excitations. If the polarization in the molecule does not couple to these other possible polarizations, then it will not change the vibrational state that the molecule started in, and the scattered photon will have the same energy as the original photon. This type of scattering is known as Rayleigh scattering, when the polarization in the molecules couples to a vibrational state that is higher in energy than the state they started in. Then the original photon and the scattered photon differ in energy by the amount required to vibrationally excite the molecule. In perturbation theory, the Raman effect corresponds to the absorption and subsequent emission of a photon via an intermediate quantum state of a material. The intermediate state can be either a real, i.e., stationary state, or a virtual state. Stokes and anti-Stokes. The Raman interaction leads to two possible outcomes. The energy difference between the absorbed and emitted photon corresponds to the energy difference between two resonant states of the material and is independent of the absolute energy of the photon. The spectrum of the scattered photons is termed the Raman spectrum. It shows the intensity of the scattered light as a function of its frequency difference delta nu to the incident photons. The locations of corresponding Stokes and anti-Stokes peaks form a symmetric pattern around delta nu 0. The frequency shifts are symmetric because they correspond to the energy difference between the same upper and lower resonant states. The intensities of the pairs of features will typically differ, though. They depend on the populations of the initial states of the material, which in turn depend on the temperature. In thermodynamic equilibrium, the lower state will be more populated than the upper state. Therefore, the rate of transitions from the more populated lower state to the upper state will be higher than in the opposite direction. Correspondingly, Stokes scattering peaks are stronger than anti-Stokes scattering peaks. Their ratio depends on the temperature, and can therefore be exploited to measure it. Distinction from fluorescence. The Raman effect differs from the process of fluorescence in that it is a scattering process. For fluorescence, the incident light is completely absorbed, transferring the system to an excited state. After a certain resonance lifetime, the system excites to lower energy states via emission of photons. The result of both processes is in essence the same. A photon with a frequency different from that of the incident photon is produced and the molecule is brought to a higher or lower energy level. But the major difference is that the Raman effect can take place for any frequency of incident light. In contrast to the fluorescence effect, the Raman effect is therefore not a resonant effect. In practice, this means that a fluorescence peak is anchored at a specific frequency, whereas a Raman peak maintains a constant separation from the excitation frequency. Selection rules. A Raman transition from one state to another is allowed only if the molecular polarizability of those states is different. For a vibration, this means that the derivative of the polarizability with respect to the normal coordinate associated to the vibration is non-zero, \frac \ni 0. In general, a normal mode is Raman active if it transforms with the same symmetry of the quadratic forms, which can be verified from the character table of the molecule's symmetry group. The specific selection rules state that the allowed rotational transitions are \delta J \PM2, where J is the rotational state. The allowed vibrational transitions are \delta \nu \PM1, where \nu is the vibrational state. Stimulated Raman scattering and Raman amplification. The Raman scattering process as described above takes place spontaneously, i.e. in random time intervals. One of the many incoming photons is scattered by the material. This process is thus called spontaneous Raman scattering. On the other hand, Stimulated Raman scattering can take place when some Stokes photons have previously been generated by spontaneous Raman scattering, or when deliberately injecting Stokes photons together with the original light. In that case, the total Raman scattering rate is increased beyond that of spontaneous Raman scattering. Pump photons are converted more rapidly into additional Stokes photons. The more Stokes photons are already present, the faster more of them are added. Effectively, this amplifies the Stokes light in the presence of the pump light, which is exploited in Raman amplifiers and Raman lasers. Stimulated Raman scattering is a nonlinear optical effect. It can be described using a third-order nonlinear susceptibility /chi. Need of space coherence. Suppose that the distance between 2 points A and B of an exciting beam is, generally, as the exciting frequency is not equal to the scattered Raman frequency, the corresponding relative wavelengths and are not equal. Thus, a phase shift appears. 4. The scattered amplitudes are opposite, so that the Raman scattered beam remains weak. A crossing of the beams may limit the path. Several tricks may be used to get a larger amplitude. In an optically anisotropic crystal, a light ray may have two modes of propagation, with different polarizations and different indices of refraction. If energy may be transferred between these modes by a quadrupolar resonance, phases remain coherent along the whole path. Transfer of energy may be large. It is an optical parametric generation. Light may be pulsed, so that beats do not appear. It is the impulsive stimulated Raman scattering, in which the length of the pulses must be shorter than all relevant time constants. Interference of Raman and incident lights is too short to allow beats, so that it produces a frequency shift roughly, in best conditions, inversely proportional to cube of length of pulses. In labs, femtosecond laser pulses must be used, because the ISRS becomes very weak if the pulses are too long. Thus ISRS cannot be observed using nanosecond pulses, making ordinary time incoherent light. Brought to you by WikiVidi Documentaries. Would you like to know more?